Hi everyone. So I decided to record these lessons since your homework on forces has problems with tension. So this is a brief introduction to tension. Let's define it. Tension is a pulling force by means of a string, cable, or a one-dimensional continuous object. One of the conditions or one of the things you'll see when we're dealing with tension is that usually the string, cable, um, is considered to be without mass or massless, meaning the mass is so small that we neglect it. It's a negligible mass, okay? It just makes the math a lot easier. So let's just run with it, massless cable. For instance, the simplest situation we're going to have is the one shown over here. An object of mass m hangs from the ceiling by means of a massless cable. Massless again. And as with forces, we draw a free body diagram, right? So I'm just going to copy the object, the shape of the object, but then after that, we don't really need to do that. We just identify the center of mass. So somewhere here, center of mass, let's draw our vectors, our force vectors. So we have the weight of the object pulling straight down. We label it. We know that the weight is the mass times the acceleration due to gravity. In the first example we had for free body diagrams, we had a book resting on the table, so we have the weight of the book, and we had the normal force perpendicular to the surface. Now we don't have a surface, thus we don't have a normal force. However, we still need a force acting against gravity as per Newton's third law of motion, because this is not a free fall. So that's where tension comes in. It's a force. So let's draw, oh, forgot to change red. We have the force equal in magnitude but opposite in direction. So let's make sure it's equal magnitude, opposite in direction. There you go, that's pretty good. And we label it as tension, so just capital T. And that's it. We have no other forces present acting on our object. So let's sum the forces. There's nothing going on along the x, so we'll just worry about the y direction. No movement, so we have 0 is equal to T plus mg. That's the tension plus the weight of the object. The only way our equation will hold true is if the tension is equal to the weight, because it's just hanging there. And that's it. Pretty simple. If we knew the mass of the object, it would be very simple for us to calculate the tension. All we do is multiply mass times acceleration due to gravity, and that's it. Now let's look at a different, slightly more complicated example. It says, fitness guy, whose mass is 100 kilograms, hangs from a tree branch with both arms. What is the individual tension on each arm? One thing to be mindful of is we have tension on each arm. Now, based on symmetry, the weight, the weight of fitness guy will be equally distributed in between both arms. So the tension will be the same, okay? And that's important when we draw a free body diagram. So let's go first, center of mass. We have the weight of the fitness guy, or the weight of fitness guy. It's a human being. So there you go, pulling straight down. And we have tension, pulling upwards. Oh, I didn't use an arrow over here. Let's do that again. There you go, that's pretty good. Let's label. We know this is the weight, mass times gravity. Now over here, we would have the tension from each arm. In other words, this one would be T plus T, or 2T. And that's very important when we draw a free body diagram. Okay? Otherwise, we're going to get the wrong answer. Now we can find the tension or each of the from each arm. Now we have to sum the forces. There's nothing going on along the x, so we just worry about the y. The guy is just hanging there, so 0 is equal to 2t plus mg. Now let's write down our given. We know that the mass of the guy, fitness guy, is 100 kilograms. Acceleration due to gravity will be negative 9.8 meters per second squared. We're looking for tension T. Let's take this part of the equation. 0 is equal to 2t plus mg. I'm going to subtract mg from both sides. Since I'm trying to find the tension, this cancels, so I have 2t is equal to negative mg. Now let's divide by 2. So we're trying to find t. This cancels, and my final equation says that tension is equal to negative mg divided by 2. All we do is substitute. T is negative, then 100 kilograms times negative 9.8 meters per second squared divided by 2. Oh, let me redo that. 2. There you go. Now notice that these two negatives are going to cancel. And then when I multiply 9.8 times 100, I move the decimal point 2 places to the right, so that'll be 980 kilogram times meter per second squared divided by 2. Notice that kilogram times meter per second squared equals, it's the same as a Newton because we're dealing with forces, so tension is measured in newtons. So tension is 980 divided by 2, 490 newtons. And there you go. That's the tension on each arm. It makes sense because both arms are holding the entire weight of fitness guy. The entire weight of fitness guy is 980 newtons, so each arm is or has a tension or is pulling with a tension or with the force of 490 newtons. Now, this example is a little bit more complicated because it deals with trigonometry. It says, after retiring from football, Darren Sproles hung his cleats with a mass of 0.2 kilograms on the middle of a 6-meter massless wire. This caused the wire to sag 4.0 centimeters. What is the tension on each side of the wire? So we need the tension here and here. Since it's placed on the middle, by symmetry, T will be the same as T. So these two tensions are the same, and that's important when we draw a free body diagram and for our final answer. I included steps provided by the guy in Flippin' Physics. Great YouTube channel, check it out. And it says, draw the free body diagram. If more than one object is present, draw a free body diagram for each object. We will do that when we have pulleys. Right now we don't. So we're going to consider the cleats as just one object, right, one mass. So let's start with our center of mass. Here's fine. Let's draw our vectors now. I'm going to take this as a reference. So there you go. Do it like that so it's easier for me to draw the second vector. And we have the other one. There you go. And last but not least, we have the weight of the cleats. There you go. Let's label them. So this is the weight, mass times acceleration due to gravity, tension, and tension. Now the second step says break the forces into components, X and Y. So we need to find the component of tension acting along the Y direction and the component of tension acting along the x direction. By symmetry, they're going to be the same, so we can focus on the left side only, and it'll translate to the right side. So I'm going to copy this vector. So I'm going to break the components individually for this vector. All right. So let's go for the component of the tension along the y direction and the component of tension along the x direction. There you go. And as you can see, we have one of our favorite shapes, right triangle. Let's do that again. There you go. And this angle over here is theta, as we usually have it. And this is the tension. Now, from our previous lessons, hopefully you remember that the component along the y, when we have a triangle like this, would be t sine theta. And when we have the component along the x, would be t cosine theta. That's based on trigonometry, and that angle theta is this one over here. The problem is that we don't have theta. But if we read the problem, we have information which can and will help us to find the angle theta. Because it says that when Darren Sproul hung his cleats on the wire, this caused the wire to sag 4.0 centimeters. So I'm going to take this free body diagram to have as a reference. And now we're going to worry about lengths. So let's erase this over here. I'm only going to focus, well, you know what? No, so let's have it like that. Now, before the cleats were there, the cable should have been just horizontal, like that. And we know this distance over here is 4 centimeters, as per the problem. So as you can see, this is symmetrical, so I'm only going to worry about this side. You'll see why in just a moment. So there you go. Very good. And this side is 4 centimeters. And this side is 3 meters. Why is it 3? Because the length of the entire wire is 6 meters. So half of it would be 3 meters. So that's important for us to notice, okay? Now this would be the 90-degree angle, and as per geometry, this theta corresponds to this theta over here. So now we can use SOHCAHTOA. This is the opposite side of theta. It's just blue. And this is the adjacent side with respect to theta. We can finally use our function or the TOA side, right? Because we never use it. We only use sine and cosine most of the time. So we have TOA. That is the tangent of theta is equal to the opposite divided by the adjacent. Before we substitute, something we should notice is that we have 4 centimeters. We don't want centimeters. We're going to use meters. Okay? And we can do a very quick, simple dimensional analysis. We have 4 centimeters. We need to get rid of the centimeters. We have to have meters at the end. So 1 meter equals 100 centimeters. We cancel this. We have 4 times 1 divided by 1 times 100 meters. That'll be our answer. It's just the same as divided 4 by 100. So that'll be 0.04 meters. So our opposite side is 0.04 meters. Now we can use tangent. So the tangent of theta is equal to the opposite, 0.04 meters, divided by the adjacent, which is 3 meters. Now let's use our calculator to see what that is. 0.04 divided by 3, 0.01333. So 0.01333. And notice we have no units because the meters cancel the meters. So now we need to find theta. And to find theta, if you remember from our previous lesson, we used the inverse tangent. Another way to call it, or for this, the inverse tangent is arctangent. Actually, mathematicians like this a lot more than inverse tangent. For me, it's you can use either or, but if you're in math class, use arctangent to make your teacher happy. But it's the same as inverse tangent. Okay, just this one has to do with arc length. So, but it's the same. So the way it works is you have you multiply inverse tangent on both sides. I'm going to write it like this strategically on the right side. There you go. This one cancels this one, so we have that theta is equal to the inverse tangent or arctangent of 0.013333. So let's do that. In our calculator, we go for the trig functions. There is inverse tangent of, I'm going to use the answer command, right? So control this one over here. Press enter. So our angle theta is 0.76. Let's write it down. Theta is 0.76 degrees. Now we have theta. Let's write our given. Have the mass of the cleats, 0.20 kilograms. You have acceleration due to gravity, negative 9.8 meters per second squared. Theta is 0.76 degrees, and we're looking for tension T. Now, we already broke the forces into components. Now we have to redraw the free body diagram with X and Y components. So we have this one over here. We're going to use symmetry. So our center of mass, as usual, we have the weight of the cleats. There you go. And then we have one component along the X, the second component along the X, there you go. And you have a component along the Y direction. Now when we label, we have to be careful because it's very easy to make a mistake over here, okay? So we know this is the weight of the object, mass times gravity. We know this is the tension times the cosine of theta. By symmetry, this is also the tension times the cosine of theta. Don't forget, we got this from our very first free body diagram. Now, if we write this one as T sine theta, that would be incorrect. The reason being is there is a component along the Y direction from each side. So this one is not just t sine theta, but t sine theta from this from the left side plus t sine theta from the right side. So this would be plus t sine theta. If you want to simplify, you can just rewrite it as 2t sine theta. There you go. Now, steps 4 and 5, sum the forces, x direction, sum the forces, y direction. So, now let me do it over here. So the summation of the forces along the x direction, there's no motion, will be equal to 0, which is t cosine theta plus t cosine theta. I'm going to leave it like that. I'm not concerned about what's going on with the x direction. I want to find the tension in a half mass and acceleration due to gravity. So I care about the y direction. Summation of the forces along the y direction still equal to 0 because it's not moving. But now we have 2t sine theta plus mg. I'm going to take this part of the equation over here. I'm going to subtract mg from both sides. I'm trying to find T for tension. So I have that 2t sine theta is equal to negative mg. So I need to get rid of the 2 and the sine theta. So everything is the relationship in between 2t and sine theta is multiplication. So I do the opposite. So I divide by 2 sine theta. So I can get rid of this, this, and this. Let's do this on the right side as well. And my final equation says that the tension on each side of the cable is negative mg divided by 2 sine theta. Now I can substitute. Tension is equal to negative 0.20 kilograms times acceleration due to gravity, which is negative 9.8 meters per second squared, and divided by 2 sine of 0.76 degrees. So let's substitute that into our calculator. So it'll be parentheses, negative parentheses, 0.2 for the mass times parentheses negative 9.8 for acceleration due to gravity, close parentheses, divided by parentheses 2, let's go for trig functions, the sine of 0.76, close parentheses, press enter, and we're gonna round up to 74. So our force is 74 newtons. The tension force, or tension, is equal to 74 newtons on each side. So we go back to this diagram. I can write that we have 74 newtons over here and 74 newtons over here. That is the tension on each side of the cable. If you wanted the tension, overall tension or total tension, you just add them up, and that's it. All right, class, so that was it for our introduction to tension. Next lesson will be on pulleys. Bye.